Today we're going to begin looking at the dot product. So to begin, when we're referring to geometric vectors, we're referring to vectors that do not have coordinate systems associated with them. So over the next few days, we're going to be learning some vector operations that are going to help us solve more vector application problems. So just for an example here, to calculate work done on an object, we're going to use the formula that our work is equal to our force acting on an object, so our vector F, dot product of S, which is the displacement of the object. So this is what we call our dot product. So what is our dot product? So as you can see here, our dot product is between AC and AB is just the magnitude of the vector AC and the magnitude of the vector AB times cos theta, and theta is between 0 and 180 degrees. So when discussing this, however, we want to know, well, when will we actually use this? How do we calculate it? So we're going to look at examples of that. But before we begin, we need to make sure that we only use it with vectors. Okay, so that's the dot product can only be used with vectors. Also, it's used to determine the work performed, and the units are in Newton meters or joules. Also, I'd like you to note here that the result is a scalar, as well as when we're looking at our vectors, you're going to set your vectors when using the dot product all the time tail to tail. When we added the vectors, we always add them tail to tip, okay? But when we're doing the dot product, always make sure that we do tail to tail. So in our first example, we want to determine the dot product of each. So you have two vectors A and B, which are placed tail to tail and have a magnitude of 3 and 5 respectively, and there is an angle of 120 degrees between them. So we have angle A and B. So this here, we're going to say it's 120 degrees, our vector A and our vector B. Now, the dot product of A and B is the magnitude of A times the magnitude of B, and in this case, the angle between A and B, which is 120 degrees. So the magnitude of A is 3, magnitude of B is 5, and cos 120. And now when we solve that, we're going to get negative 7.5. Well, what does that negative mean? That negative means there's negative work. Okay, so let's look at part B now. So when we're looking at B here, if the magnitude of A is equal to 10 and the magnitude of B is equal to 5, and the angle between the vectors is 40, so we want to find the dot product of A and B. So what we have here is A and B, and the angle between them is 40 degrees. So the dot product of A and B in this case is equal to 10 times 5 cos 40. When we calculate this, we're going to get 38.3. Therefore, we have a positive work. Okay, so the dot product is going to tell us if it's negative or positive. But let's look at C here. So we have unit vectors. Unit vectors magnitude. Recall that the magnitude of any unit vector is always going to be equal to 1. So, and we know the angle between them is 90 degrees. Therefore, they are what we call perpendicular. So the dot product between A and B is equal to 1 times 1 cos 90. Cos 90, recall here, is 0 degrees, so 0 times 1 times 1 is just going to be 0. So therefore, when perpendicular, we have this equal to 0. Okay, so therefore, there is no positive or negative work. So note here, the answer is always a scalar. And also the dot product can be positive, negative, or 0. So we looked at 3 different examples of that. Also, one of the most important observations to be made about the dot product is that when two non-zero vectors are perpendicular, their dot product is always going to be 0. So like we saw in part C here. And also talking about the sign of the dot product. So for the vectors a and b, the dot product of a and b is the magnitude of a times the magnitude of b cos theta, where theta is between 0 and 180 degrees. So when we're looking at theta where it's between 0 and 90, such as in example B, cos theta here is going to be greater than 0. So therefore, the dot product of A and B is also going to be greater than 0. Now, when we're looking at an angle measurement of 90 degrees, so like in part C, cos theta is equal to 0. Therefore, the dot product is equal to 0. And for theta being between 90 and 180, so as we saw in part A, cos theta will be less than 0, so therefore our dot product will also be less than 0, giving us negative work. Now what I would like you to do is I'd like you to pause the video and go through the investigation on the next 2 pages on your own. And then when you're done, you can restart the video and we will go through the examples together. But make sure that you remember when we are doing the dot product, it's tail to tail. When we are adding vectors, it's tail to tip, as well as looking at your different properties that may exist. So please go through the investigation. I will have the solutions ready for you guys in class tomorrow. However, I want you to see that you guys have tried to do the investigation on your own. So hopefully you got that investigation done, and we will now look at example 2a. So in 2a, if the magnitude of A is equal to the square root of 7, we want to calculate the dot product between A and A. So if we're talking about the same vector, I know my angle measurement between that vector is going to be 0. So when we're talking about the dot product between A and A, we're looking at the magnitude of A times the magnitude of A cos 0, which is going to be equal to the square root of 7 times the square root of 7 times 1. Therefore, when we multiply that, we're going to get 7. In part B, we want to calculate the dot product between I and I. What is I? Recall here, I is just our unit vectors. Okay, and the unit vector of I, okay, the magnitude, is going to be 1. We know that. So let's look at the dot product between our unit vectors. So we're looking at the magnitude of I times the magnitude of I cos 0, because it's the same vector. So this will be equal to 1 times 1 times 1, therefore it's equal to 1. So some properties that do exist of the dot product, so through your investigation you should have found this. So when we're looking at the commutative property, so all this means is that if we're taking the dot product between P and Q, you can have the dot product where P is your first vector dot Q, or vice versa, Q dot P. Now the distributive property, so just as it says, you're going to distribute into the brackets. So the dot product of P and Q plus R is just equal to the dot product between P and Q plus the dot product between P and R. Also, looking at our magnitudes property, so the dot product between a vector and itself is just equal to the magnitude squared. And also looking at our associative property with a scalar k, if we have the scalar k times our vector p, okay, and the dot product between that and q, we have this equal to the dot product between P and the scalar K and the vector Q, or you could just find the dot product between P and Q and then multiply it by K at the end. So now let's look at example 3. So now in example 3 of the vectors A plus 3B and 4A minus B are perpendicular. So if they're perpendicular, we know that at 90 degrees, because that's what perpendicular means, cos 90 is equal to 0. And A, so the magnitude of A, is equal to 2 times the magnitude of B. We want to determine the angle to the nearest degree between the non-zero vectors A and B. So what we're going to do here, we are going to do the dot product between A plus 3B, dot product there, and for A minus B, which is equal to 0. We're going to set that equal to 0 to be able to solve for our angle between them. So here we can use our distributive property. So what we have is the dot product between A and 4A minus, okay, so now you're multiplying between the dot product of A and B plus the dot product between 3B and 4A. So 3 times 4, you can just multiply those together to get 12. And that's going to be B, the dot product between B and A there. And then our last one here, the dot product between 3B and negative B. So negative 3B, dot product between them. Okay, and it's equal to 0. Using a couple more of our distributive properties, or sorry, our other properties of dot products, what we have here, so if I just want to rearrange this, if we have 4 times the dot product of A and A, here we can change, so we have the dot product between A and B. We can change this one here, our 12, be the dot product between B and A, to having it as A and B. So that comes from our commutative property. So that's 12 A, B. And then here we're going to have minus 3 times the dot product of B and itself equal to 0. So now looking at our magnitudes property, when we are taking the dot product between a vector and itself, that is just going to be the vector itself, the magnitude of it squared, plus, so we're going to collect like terms here, negative, there's like a phantom 1 there, so we have plus 11 and the dot product between A and B. And then same here, magnitudes property, minus 3, and the magnitude of B squared is equal to 0. So we can just do a little bit of side work. We're going to come back to this, but just using the fact that we know the magnitude of A is equal to 2 times the magnitude of B. Now if I were to square this, okay, but somehow I need to get rid of either the magnitude of A squared or the magnitude of B squared, because we want everything in like terms. So if we take the magnitude of A squared, you're squaring both sides here, we can square our right hand side too. So this tells me the magnitude of A squared is equal to 4 times B squared here. So I'm going to replace my A squared with my 4B squared. So I have 4 times 4 magnitude of B squared plus, here I'm going to also change my A here Okay, so this A, so that is in terms of B. So we know it's given here that the magnitude, oh sorry, I'm not going to change that yet. I'm skipping ahead one step before doing the dot product. Sorry, we should look at the dot product here. The magnitude of A times the magnitude of B, then we'll be able to do it in the next step. Cos theta, and then minus 3 and the magnitude of B squared is equal to 0. I can multiply 4 times 4, so I get 16 times the magnitude of B squared. I'm going to bring that negative 3B squared over because I'm going to collect these in my next step. You can collect them in that step before. I just want to show every single step here. So plus 11. Now here's where I can change the magnitude of A. Okay, using the fact that I know the magnitude of A is equal to 2 times the magnitude of B. So I have 2 magnitude of B times the magnitude of B cos theta, and that's going to be equal to 0. So 16 minus 3, I'm going to get 13 times the magnitude of B squared plus 22 magnitude of B squared cos theta is equal to 0. So you can see everything's working out nicely here. Now some people might say, oh, I can collect the 13 and 22. You can't do that because of the cos theta here. Okay, our first term doesn't have a cos theta, so we need to rearrange because we need to solve for that theta. So I'm going to keep my 22 times my magnitude of B squared cos theta on my left side. I'm going to bring that 13 over, so it's going to be minus 13 times the magnitude of B squared. Divide both sides by 22 magnitude of B squared. So when I do that, I'm left with just, I'm going to continue up here, I'm left with cos theta is equal to, these B squareds cancel out, perfect. It's equal to negative 13 over 22. When I put that in my calculator, I do the inverse of cos, I'm going to get that theta is equal to 126 degrees because it tells me I want it to the nearest degree. And that's example 3.